Hello everybody, and welcome to our next lecture dealing with sedimentary environments and rocks. So away we go. Alright, so our objective is number one, how do sedimentary rocks form? Well, we discussed that previously. Next, what are the different types of sedimentary rocks? We've also covered that so far. So now we also need to think about things like what are the different layers and features of sedimentary rocks. So we're going to think about things like sedimentary structures and how they form. We're also going to think about what are the environments in which sedimentary rocks form, and that's going to be the focus mostly of this lecture. And we're also going to think about how do we study sedimentary rocks, infer environments, and reconstruct changes in the environment. So we've already covered this, so we're not going to really focus on it too much. Of course, as I'm sure you remember, a sediment will be deposited, it will be compacted. In some cases it can be cemented to form the sedimentary rock, or in more extreme cases it can undergo the process of diagenesis, which is of course when the minerals in the rock are altered. That will of course produce the all-important minerals that lock together, producing a nice robust sedimentary rock. But the moral of the story is this process of compaction, cementation, and maybe diagenesis produces a sedimentary rock from loose sediment, and that process is referred to as lithification. So this diagram was also seen in previous lectures. So if you remember, up at this point, typically in higher terrain, we'll have both physical and chemical weathering of the rock. This will cause the rock to break down and fall to pieces, essentially. The pieces will then be transported. During transportation, there will be erosion of the clasts. This will cause the clasts to change in shape, change their size, change their sorting, but also change chemically as well, and we'll touch on that today. Now, the speed at which these processes take place is a reflection of the energy of the system. The more energetic the system, the faster your pieces of rock will be rounded, the faster they will change in size, and the faster they will become better sorted. Now, eventually, after they've been transported, the transporting medium, remember there's four of them: water, wind, ice, gravity. The transporting medium will essentially lose energy. It will have to deposit the sediment. The sediment will be deposited as typically a horizontal sheet. Over time, more and more layers of sediment will be deposited, pushing layers deeper and deeper into the stack. As they get pushed deeper and deeper into the stack, pressure and temperature increase. As pressure and temperature increase, that's when we get the compaction, then the cementation, and finally the diagenesis, which on this diagram is referred to as recrystallization. And at that point, once we cement our rock or recrystallize it, diagenesis, we end up with a sedimentary rock. It's no longer a sediment, it is a sedimentary rock. Okay, so what things do rocks actually show us? Well, there's a few things that we can see when we look at a rock that's actually quite helpful to a geologist. So the first thing we're going to see is obviously the colour. Now, most of the time, the colour doesn't really tell us that much. I mean, most rocks that contain clay and silt will typically be grey or maybe a grey-red in colour. Typically, most rocks that contain sand will often be a kind of very light beige colour, but there are some times when the colour of the sedimentary rock can be helpful to us, and there's typically two occasions when that occurs. The first occasion is when we have a rusty red rock like this. Normally, rusty red rocks will be forming in desert or semi-desert conditions. So when we see a rusty red rock like this, as a geologist, instantly think, okay, this rock could have formed in a desert. Now, I am going to point out that also rocks that form in very, very, very deep marine environments on the abyssal plain can also have a red colour to them. So the red colour doesn't always mean they formed in a desert, but it's a good indicator. The other colour that we keep an eye out for is green. Green will typically mean the rock has formed in a marine environment. So if you have a mudstone and it has a slightly green tint to it, that can also be an indicator that it formed underwater in the marine environment. Once again though, it's not a hard and fast rule. You can get rocks that are green in colour which did not form in the marine environment, but it's a good starting point. Now, in terms of size, shape and sorting, we've already gone and discussed this, but typically, the way to think about it is this. Number one, the larger the clasts, the more energetic the system has to be, because you need high energies to move those clasts. So if you see a sediment that contains really, really big pieces of rock, the system, the environment in which that sediment was deposited and transported must have been energetic. Okay, it must have been something like a fast-flowing mountain river or a beach being hit by big, powerful waves. On the other hand, it could not have been a desert, because a desert is, a relatively moderately powerful environment, but it could never move big, heavy pieces of rock. Of course, we've also discussed how the shape of the rock will change over time. As the sediment gets transported, the rounder the rock will become. So, if you have a sediment that contains nice rounded clasts, that will typically suggest the sediment has been transported for a long time, and therefore the sediment has been deposited a great distance from the sediment source. In contrast, if the clasts in your rock are angular, that will typically suggest the sediment has not been transported very far, and so that would mean the environment of deposition is relatively close to the sediment source. Now, if we just go back for a second, we've already touched on the fact that the vast majority of sediments are going to be formed in a mountainous terrain. And so if we have a rock that has lots of angular clasts, well, that would suggest we are relatively close to our sediment source, so we're still going to be in this mountainous or semi-mountainous terrain. In contrast, when we have a sediment that's got very well-rounded clasts, well, that would typically suggest we're dealing with an environment that's quite a long way from the sediment source, so we're going to be all the way over here. So looking at the clast roundness is also important, but we also need to remember, and we've touched on this already, clast roundness is also a reflection of energy. So if you have a system that has sediment that has very, very large clasts in it, but those clasts are quite well rounded, well, that would suggest that you are probably dealing with a high energy system, and that high energy system is probably quite close to the source. So you might be dealing with something like a mountain river. Now, then we have to think about the thickness of the beds. So, once again, this isn't a hard and fast rule, so don't take this as gospel. But the thicker the beds, typically, the more sediment is being deposited to make that bed, which kind of makes sense. So, if you have a big, thick bed of rock, well, that typically means it cannot have formed in a low-energy environment. Most low-energy environments will typically form very, very thin layers of rock. In fact, sometimes they're so thin we call them laminations. That's a specialist term for very thin layers. So normally when we have a sequence that has lots and lots of very, very fine layers of rock in it, we would typically assume that that is formed in a relatively low energy environment. In contrast, if we start seeing big, thick layers of rock, we would normally assume that is a slightly higher energy environment. Once again, not a hard and fast rule, but it does give us a possible indicator. Now, then we'll look at the type of bedding. Now, at the moment, we're not going to worry about the type of bedding too much. That's something that's going to come in following lectures. But it's worth pointing out that there are typically a couple of different types of bedding. So sometimes there are beds, and you can see a bed here, where we have a nice, sharp gradation between this bed here and this bed here. Now that's referred to as a sharp contact. On the other hand, if we look at this bed here, we can see that this bed here, this red one, kind of slowly merges into this grayer layer above. That's called a gradational contact. So you can have sharp contacts and you can have gradational contacts, and that tells us something about how the sediment was deposited, and therefore what type of environment the sediment was deposited into, what type of environment the sediment was deposited from, what type of system. And so that's going to give us, once again, some indicators that as a geologist we can use to try and work out what process deposited the sediments, and therefore what environment the sediment was deposited in. Then there are going to be things like sedimentary structures, and in this picture you can see we have some mud cracks. So something like a mud crack is going to tell us something about the system itself. So the mud, when it initially starts, has to be quite wet. And then the mud has to dry out relatively quickly, and as it dries out relatively quickly, the surface will crack. So mud cracks are typically associated with environments where you have wet muddy sediment being deposited, followed by a relatively fast period of drying, so you'd expect it to happen in a dryish environment. So somewhere like Houston, Texas is a great example of that kind of situation. You can have a situation where a bayou dumps its muddy sediment when it's flooding And then when the floodwaters retreat, the muddy sediment is left exposed, and it will dry out very, very quickly, and it will form these mud cracks. And then the mud cracks can be preserved in the sediment, and as a geologist we can come along later and we can see these mud cracks in the rock, and that gives us some kind of indication about what type of environment the sediment was deposited into. The final thing, of course, are fossils. Fossils are extremely helpful to us. So any rock that's after 541 million years ago is typically going to contain, if we're lucky, a fossil of a hard-bodied organism, which will allow us to work out approximately what type of environment this sediment was deposited into. So, if we're finding things like marine fish fossils, well, we know it's been deposited into the ocean. If we find freshwater fish fossils, we know it's been deposited probably into a lake. If we find plants like this, we know it's been deposited into a swampy environment. So there are lots of different types of fossil that we can find that give us really, really good indications of the types of environment in which the sediment was being deposited. And so that helps us work out the environment of deposition and what was going on. So why is this really important to us? Well, we need to remember that the Earth is a constantly changing system. And this means that the climate experienced at any point on the Earth's surface has changed over time. So this means the climate that was experienced in the Houston area, 10 million years ago will not be the same as the climate we have now. And so this is obviously going to affect the environments of deposition. So over time, the environments of deposition at a given point on the Earth's surface will change. And so this means that over time, the types of rocks being deposited will also change, because remember, the sedimentary rock being deposited is a direct reflection of the environment of deposition. If you're in the ocean, you're going to get a rock associated with a marine environment. If you're on land, you're going to get a rock associated with some kind of continental environment. And so that means if we look at the rock record of an area, that will give us essentially a sequence of events through time. So let's have a look at this stratigraphic column here. So this is the stratigraphic column for the canyon walls of the Grand Canyon. Now, the first thing I want you to take a note of is if we have a look here, we have Cambrian, Devonian, Mississippian, Pennsylvanian, Permian. You can quite clearly see we are missing the Ordovician and the Silurian between the Cambrian and Devonian, so we know that this is obviously going to have to be an unconformity here. We've lost rock. Okay, so just bear that in mind. This isn't a complete sequence, but it is a pretty good sequence. So the stratigraphy in an area represents the sequence of events that have occurred. So as a geologist, we will go to the oldest rock first. If you remember, principle of superposition says the oldest rock will typically be at the bottom, and the youngest rock will typically be at the top. And so what we're going to do is we're going to look at this sequence for the Grand Canyon, and we're going to see how we can use it to work out the sequence of events for that area. Alright, so we're going to start off down here with the Vishnu schist. Well, those are metamorphosed rocks. We're not going to really talk about those. They've been quite badly mucked about with, geologically speaking, so we're just going to ignore them for now. So then we're going to come into the Grand Canyon supergroup, which I've called the GCS here. This is a sequence of marine sediments. So these sediments have all been deposited underwater. Now, they have been lightly metamorphosed, so once again, they're not the original sedimentary rocks, but we can see from them that they are of a marine origin. Alright, so now we're going to come up here to the Tappet Sandstone, and this is a mixture of beach sands and shallow marine sand, so just off the coast. So we can see when this layer was deposited, we were in a coastal environment. Now then we come up here to the Bright Angel Shale. When this sediment was deposited, we can see we are now in a marine environment because these are marine muds. So what does this tell us? Well, it tells us between the deposition of the Tappet Sandstone and the deposition of the Bright Angel Shale, well, the sea level's gone up. What was a coastal environment has now become a fully marine environment. It's been covered by the sea. So we can see the sea level depth increasing. What's next? Well, now we have the limestone, and we can see once again, in this case, this is a marine limestone, like nearly all limestones, and this is another indicator that the seawater depth has gotten even deeper. So we've gone from shallow seawater here to moderate seawater here to deeper seawater here. So we can see the areas being covered over by more and more seawater, which suggests that sea levels are obviously on the rise during this time period. So that's telling us something about what's happening at this location in the Grand Canyon area. Now obviously we're missing the Ordovician and the Silurian, and so this tells us that any rocks deposited during that time period have been eroded away. So that typically would suggest that sometime during the Ordovician and the Silurian, the area has been above sea level, so it's been exposed to the atmosphere, and when the rocks are exposed to the atmosphere, well, that means they can be eroded and lost. Anyway, so we're going to go on to the Devonian now. The Devonian is represented by the Temple Butte Formation. So the Temple Butte Formation is a sequence of shallow marine carbonates, and in fact this red line's pointing to the wrong location. It should be pointing right here. Oops, my mistake, I do apologize. So the Temple Butte Formation is a sequence of shallow marine carbonates that are filled in paleo valleys. So a paleo valley, as the name suggests, is a valley. And the paleo valleys will have been left by rivers, and then what's happened is the sea level has gone up, and as the sea level has gone up, those river valleys have bnow filled up with seawater, and within those river valleys we've had shallow marine carbonates being deposited, and that's what the Temple Butte Formation is. So once again, we now know we're back underwater again in a shallow marine environment. Then on top of the Temple Butte Formation we have the Red Wall Limestone, and that once again is a sequence of shallow marine carbonates, so we know we're still underwater, and once again we know we're in a carbonate system. I do apologise if you can hear my dog barking. That's Rupert protecting the house from who knows what. Okay, so next we have the Sipai Formation over here, and to begin with we're going to start with a sequence of erosional and fluvial rocks. So fluvial of course means river. So at the bottom of this sequence here we have ourselves a pile of river rocks. So we're now above sea level, and the area is now covered by large rivers. That's then followed by a sequence of desert, fluvial, beach and shelf deposits. So it's a bit of a mixture here for this sequence of the Sipai group. And so what's going on? Well, at this point we have the sea level fluctuating up and down, which means sometimes during the Pennsylvanian the area was essentially covered in seawater, and at other times it was exposed land. So during these time periods when the land was exposed, it was either a desert or it was covered in river systems. Sometimes it was coastal, so we have beach systems, and sometimes it was underwater, so it was being covered by shelf sediments, a mixture of sands and occasionally muds. So you can see during this period the sea level was fluctuating quite a lot, so it got a bit complicated. So then we're going to continue up here into the Hermit Formation. Well, the Hermit Formation is a continuation of the Sipai group, so you can see we have fluvial, desert and shallow marine sediments as well. So, these fluctuations in sea level have continued from the Pennsylvanian into the Permian. Then we have the Coconino Sandstone, and this is a pure desert sandstone. So by this point we can see we are now in a wholly desert environment, so the fluctuations have stopped, the area is now completely desert. Then the Coconino Sandstone is followed by the Tappet Formation, and this is a mixture of shallow marine sands and limestones, and a mixture of evaporites as well. So what this is telling us is we have the desert of the Coconino Formation being followed by shallow marine sediment. So once again the sea level has gone up, the area has been covered by seawater. But what we can also see is at times this seawater that's covered over the area has become isolated, it's become trapped. And so when this seawater becomes trapped, it's evaporated away and it's left behind the minerals that were dissolved in the seawater. So it's left behind minerals like gypsum and halite. And so this is telling us that we have a situation where the sea level is going up, maybe retreating every once in a while, leaving behind a trapped body of seawater when it does retreat, and that trapped body of seawater has evaporated away, leaving behind the evaporites. So once again we have a complex situation. And finally, we have the Kaibab Formation, and this is a mixture of shallow marine sediments, once again a mixture of sandstones and limestones, and so now we are once again completely underwater and in a shallow marine environment. So you can see that when we look at this sequence of rocks for the Grand Canyon, you can see we have quite a substantial sequence. So we have the start of the Cambrian down here about 541 million years ago, coming all the way up to the kind of the latish Permian, so about 252 million years ago. So that's quite a substantial sequence of rocks that we have. And by looking at the sequence, going from the oldest sedimentary rocks down here to the youngest sedimentary rocks up here, you can see we've got an idea of what was happening in this area during periods of geologic time. And this is the power of looking at a sequence of sedimentary rocks at a location. It really gives you that story. It lets you see what was going on at a given location during Earth's history. Okay, so what are we going to focus on today? Well, we're going to focus on the environments of deposition. So we're going to have a look at several different modern environments of deposition, the types of sediments that are deposited in those environments of deposition, and exactly the kind of stuff that we look for when we go and look for rocks. So the indicators of modern environments that we see today are exactly the types of indicators that we look for in the rock record. And we're also going to have a think about ancient rocks and sedimentary features, so things like bedding, rock layers, formations, and sedimentary structures. Although, to be honest, we're not going to focus on that too hard today. That's more coming in the next lecture. All right, so before we start looking at anything else, we're going to have a quick look at this slide here. Then we're going to stop the presentation, and then we're going to follow on in part 2. So, all right, so let's have a look at what we've got here. So as you can quite clearly see, here is a nice conglomerate. You can see, we know it's a conglomerate, so here's a Sharpie for scale. So we can see that the clasts are quite clearly in excess of 2 millimeters. So we know this has to be either a conglomerate or a breccia. When we look at the roundness of the clasts, well, we can quite clearly see the clasts are, well, rounded, this clast here, to sub-rounded, like this clast here. So we know we're dealing with a conglomerate. Remember, a breccia must have angular clasts. So what we have here is we have ourselves a conglomerate, and so we need to try and work out what type of environment that conglomerate formed in. Well, here we have a couple of pictures of modern sedimentary environments. So the first thing is which of these two environments likely represents this conglomerate here? Well, let's have a look at this environment here. You can see we have a poorly sorted sediment, so we have a range of larger class sizes going all the way down to small class sizes. Well, once again in this picture here we have large class sizes going down to smaller class sizes. All right, so that matches. However, when we look at the clast shape, we can quite clearly see these clasts are angular and these clasts are quite clearly not. And so that would be a very strong suggesting, that would be a very strong piece of evidence to suggest that maybe the environment we see here is not the environment into which this sediment was deposited. So what about this sediment over here? Well, once again, there's our Sharpie again. And we can see, well, in this instance, we have ourselves a poorly sorted sediment with quite nice rounded clasts. What do we have here? Poorly sorted sediment with nice rounded clasts. And so if we know which environment this picture represents, it could represent a fast-flowing mountain stream, or it could represent a quite energetic beach environment where we can say, okay, based on the similarities between this rock here and this modern sediment here, we can suggest there's a good chance that this rock may have formed from sediment deposited in this environment of deposition many millions of years ago. And so that's what we're looking for as geologists. We're looking and we're going to modern environments of deposition, looking at the sediments being deposited there, looking at the structures and the fossils that we find, and then applying that information to rocks that we find in the rock record in the hope of trying to work out what environment of deposition the sediment was deposited into. Alright, so we're going to stop here with this part of the presentation. So once again, please stop, go and get yourself some water, cup of tea, cup of coffee, and then come back when you're ready for the second part.